Okay, now for something completely different, or at least it'll seem different at first. It's called the binomial theorem. Now, to introduce this, let's do some expanding here. So I'll explain why we're doing this in a second. Okay, let's just do this first. It's fun. A plus B is a binomial, right? This is why it's called the binomial theorem. All these are binomials. It's all A plus B. So what's A plus B to the 0 power? Well, anything to the 0 power is 1. What's A plus B to the first power? Well, anything to the first power is just the same thing. So A plus B. A plus B squared. Well, that's the same as A plus B times A plus B, right? And by this point, you probably don't need to do all the mountains and all the valleys. You know that it's A squared plus 2AB plus B squared. If you don't know how I did that, A times A is A squared, A times B is AB, B times A is another AB, so those go together, get 2AB, and B times B is B squared. Okay, we deal with this all the time. This is one we don't do so often. A plus B cubed. What would be the fastest way to do that? Well, A plus B cubed is the same as A plus B times A plus B. Well, look, that's just the same as what we already did, times another A plus B. So in other words, what we could do is take this answer, this A squared plus 2AB plus B squared, and multiply it by another A plus B. So let's do that. I don't think we can do that one in our head, so we're actually going to do all the mountains and valleys. How many mountains and valleys this time? Oh, 3 mountains. 1, 2, 3, and 3 valleys. Oh goodness, we're going to be here all day doing this. All right, here we go. A times A squared is A cubed. A times 2AB equals 2A squared B. A times B squared is AB squared. B times A squared is BA squared, but let's put it in order, alphabetical order, A squared B. B times 2AB is 2AB squared. And B times B squared is B cubed. Alright, now we can combine some terms here. The A cubed can't combine anything with anything, but the 2A squared B can combine with this A squared B to get 3A squared B. The AB squared can combine with the 2AB squared to get 3AB squared, and we have the B cubed. Now, why are we doing this? Well, here's what I want to do. I want to highlight all the coefficients. So we have 1, then we have 1 and 1, and then we have 1 and 2 and 1, and then we have 1 and 3 and 3 and 1. Why are we doing that? Well, we'll soon see. Be patient, be patient. Next thing we're doing, which seems completely different, is I want to take a look at what we did last time, which was combinations. I'm going to do 4 of them here. 3 choose 0. So this means you have 3 things and you have to choose 0 of them. How many ways are there to do that? There's only one way to do that, by choosing nothing. 3 choose 1. How many ways are there to do that? 3 ways. You can choose the first one, the second one, or the third one. 3 choose 2. How many ways are there to do that? Well, let's think about that for a second. If we call the 3 things x, y, z, and we're choosing 2, you could choose x, y, you could choose x, z, or you could choose y, z. And that's it. Remember, order doesn't matter with combinations, so ZY is just the same as YZ, so there's only 3. So I'm going to get rid of that, and I'm going to put 3 there. And 3 choose 3. I've got 3 things, I need to choose 3 things. How many ways are there to do that? Just 1. Do you notice anything here? Well, I hope so. I hope that what you notice is that these numbers here are the same as these numbers here. And in fact, all these coefficients here, we can get them all by using something called Pascal's triangle or using the binomial theorem. So what's the binomial theorem? It's a method for expanding an expression of the form a plus b to the nth power. In other words, expanding a binomial, this is a binomial, where n is a whole number. This can be anything. This n here can be a small number like 2 or 3. It can be a big number like 57 or 100,000. The binomial theorem helps us to do this relatively quickly. Now I'm going to introduce you to one of the coolest things in math. It is so awesome. It's called Pascal's triangle. This was discovered by Chinese mathematicians thousands of years ago, I think it's safe to say. Maybe that's too strong. Maybe I should say hundreds of years ago. Anyway, and then Blaise Pascal, a very, very famous mathematician. Some of you wrote the Pascal math contest years ago, named after Blaise Pascal. He figured out a lot of the patterns that exist in Pascal's triangle. Pascal's triangle is really, really easy to make. You start by putting the number 1. Then we're going to make a triangle shape. I put 1 and 1. Then there's one term in the first row, 2 in the second row. In the third there'll be 3. It goes 1. You're probably thinking it goes 1, 1, 1. It doesn't. It goes 1, 2, 1. I'm just going to do a few more. I want to see if you can figure out how I'm getting these numbers. Next one should have 4 terms. It goes 1, 3, 3, 1. Okay, I'll do one more and then we'll see if you can figure it out. It goes 1, 4, 6, 4, 1. Now I invite you to pause the video if you haven't figured it out yet and try to figure out how I'm getting each number. Alright, you didn't pause the video, but you should have. And I hope you got it. How you get the next number is, for example, if I wanted to get this number here, this 3, what I do is I take a look at the two numbers on top of it, a little bit to the left, a little bit to the right, add them together, I get 3. To get this 6 here, I add together this 3 to a little bit to the left, the 3 a little bit to the right, you get 6. So let's do a couple more rows to make sure you got it. Always start with a 1. This term right here will be 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and we end with a 1. Always start and end with a 1. I'll do 2 more, I think. 6, 15, 20, 15, 6, 1, 1, 7, 21, 35, 35, 21, 7, 1. Alright, there are some pretty awesome things to notice about this triangle here. There's patterns all over the place. If you are interested in this, I invite you to take a look on the internet. You'll find so many cool patterns in this, or try to find some for yourself. For example, build one of these and then color in all the odd ones one color and all the even numbers another color. It's pretty cool. Let's look at diagonals. The first diagonal isn't very interesting. It's all ones. The second one's not much more interesting. It's just the counting numbers, 1, 2, 3, 4, 5, 6. The next one's kind of cool. This is all the triangular numbers, 1, 3, 6, 10, 15, 21. Don't know what a triangular number is? Don't write this down, but I'll just show you. Triangle numbers are like this. You can make a triangle with 1. It's not much of a triangle, but kind of. You can make a triangle with 3. You can make a triangle with 6. 1, 2, 3, 4, 5, 6. You can make a triangle with 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it goes down there. Those are all triangular numbers. Not impressed with that? How about this one? If you take a look at each row, it'll tell you all the powers of 11. 11 to the 0 power is 1. 11 to the first power is 11. 11 to the second power, you know what 11 times 11 is? 121. 11 to the third power, you probably don't know what that is, but now you do, 1,331. And this continues on and on, although it does get a little bit more complicated when you have 2-digit numbers. You have to start combining numbers, like carrying. See if you can figure it out. But I want to keep moving. What else? Well, now we get to some things that are more important. So far the things I've shown you are just kind of interesting facts, but now we need to look at things that will help us with the binomial expansion. So the next thing I want to do is I want to look at the sum of each row. So the sum of the first row is 1. The sum of the second row, 1 plus 1, 2. Sum of the next row, 1 plus 2 plus 1 is 4. Sum of the next one, 1 plus 3 plus 3 plus 1, that's 8. Next one, 5, 11, 15, 16. Are you noticing anything in these numbers? Next one, 20. Another 10 is 30, plus 2 is 32. I can tell you the next one's 64. I can tell you the next one's 128. What are these numbers? These are all the powers of 0. 2 to the 0 power, 2 to the 1 power, 2 to the squared, 2 cubed. So, you might notice that you keep having 0. We actually call this first row here, that 1 by itself, this is row 0. And then the next row, the 2 ones, this is row 1. Same with each element in the row. Like this is the first, this is the 0th term. I know we've probably never used that before, 0th. But we call that the 0th term, and then this is the first term here, and then it goes second term there, etc., etc. The first element or first term. Okay, now let's take a look back here again. Take a look at the coefficients. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Oh my goodness. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Pascal's triangle gives us all the coefficients in a binomial expansion. So if you wanted to know for an expansion like a plus b to the 5th power, what the coefficients are out front of each term, all you do is go down to the 5th row, but remember it goes row 0, 1, 2, 3, 4, 5. Oh, the coefficients are going to be 1, 5, 10, 10, 5, 1. That's how they'll go. What else? Oh, another amazing thing about it, and that's what this shows you. This 1, 3, 3, 1. You see how those numbers showed up right there? The Pascal's triangle can also be used to help you with combinations, just like we did last time. So, for example, if we wanted to know, if we wanted to know what 7 choose 3 is, of course you could pick up your calculator or you could write out the formula, but how about doing this? Okay, this is row 0, 1, 2, 3, 4, 5, 6, 7. This is 7 choose 0. This is 7 choose 1. This is 7 choose 2. And this right here is 7 choose 3. It's in the 7th row, because remember 0, 1, 2, 3, 4, 5, 6, 7. And it's the 3rd term, because remember 0, 1, 2, 3. 7 choose 35 is 35, I promise you. How about, I don't know, 4 choose 3. Okay, 0, 1, 2, 3, 4. This is the 4th row. So, and then choose 3. 0, 1, 2, 3. 4 choose 3 is 4. Done. Pretty cool. What else can we say about it? The sum of each row is 2 to the n, so that's what we showed you there. The number of terms in each row is n plus 1. So there's one in row 0 there's 1 term, in row 1 there's 2, in row 7 there's 8 terms. And that's always 1 more than the power of the binomial. So if you were expanding this, a plus b to the 5th, you would expect 6 terms. There would be 6 terms, just like a plus b to the 3rd has 4 terms. A plus b to the 1st has 2 terms. A plus b to the 0 has 1 term. There's always 1 more. And oh, here's the last thing we need to recognize, and then we'll be good to go. Take a look back up here. I know I'm going up and down, I'm sorry. Take a look at the a's and the b's. The a's start with a cubed in the 1st term, and then a squared in the 2nd term, and then a1 right here, and then there's no a here. In other words, it's a to the 0 in that term. The b's, there's no b here. In other words, it's b to the 0. Then it goes b to the 1, then b to the 2, and then b to the 3. You see what's happening? In a plus b to the nth power, a decreases from a to the n to a to the 0, and b increases from b to the 0 to b to the n. If we wanted to expand this, 2x minus 3 to the 4th power, one way we could do it, and believe me, we will not be doing this, is we could figure out what's 2x minus 3 times 2x minus 3 times 2x minus 3 times 2x3, do mountains and valleys, and then do it again with the next one, then do it. I mean, that is going to take us a long time. Or we could use one of these two methods. I like the Pascal triangle method. As long as the exponent, in this case it's 4, as long as it's lower than about 7 or 8, Pascal's triangle is good. And you know what? It's almost always going to be lower than 7 or 8, because otherwise you're going to have to write something that goes like across your page. So I think the Pascal's triangle method almost always works. Let's look back at Pascal's triangle. If we're interested in expanding it to the 4th power, then what we'd be interested in is the 4th row of Pascal's triangle. So let's go down here and figure out where is the 4th row of Pascal's triangle, and then I'll highlight it in a hot pink. Remember, this is row 0, 1, 2, 3, 4, right here. These are going to be the coefficients that we're going to put in our question. 1, 4, 6, 4, 1. Why don't I just right now write them on another page so I don't have to keep coming back and forth and back and forth. 1, 4, 6, 4, 1. Those will be our coefficients. Coefficients equal 1, 4, 6, 4, 1. One last thing to notice about the Pascal's triangle is how it's symmetrical. See, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10. It goes up, it comes down, goes up and comes down. So it's also useful to know. Okay, so for the Pascal triangle method, we have our coefficients. To do these expansions, it's of the form a plus b to the nth power. Well, what's a then if this is what we're trying to expand? A is 2x. What's b if this is what we're trying to expand? B is negative 3. And what's n? N is 4. Whoops, n equals 4. So the way it works is we take the first coefficient, which is 1. Then we write down our a value, which is 2x. Remember that the exponent on that a is going to start at 4, and it's going to go down to 0. So first of all, it's 4. The second one, which is the b value, negative 3, is going to start with an exponent of 0. Okay, that's our first term. Second term, we take our coefficient, which is 4. We write our a value, which is our 2x. We put it not to 4 now, we put it to 3. Then we take our b value, negative 3. Doesn't go to the 0 power anymore, it goes to the first power. That's our second term. How many terms should we have? Well, if there's a 4 here, we should have 5 terms. So we got 3 to go. Take our coefficient, we're on the third term, so it's 6. The a value is 2x still. It's gone from 4 to 3 to 2. The b value is negative 3. It's gone from 0 to 1 to 2. You see they always add up to 4, just like the power was there. 4, 3 plus 1, 4, 2 plus 2, 4. 2 to go. Take our coefficient, which is 4. A value is 2x. It's going to have a power of 1. Negative 3 is going to have a power of 3. It's moving up. Plus coefficient of 1. A value is 2x. It's now going to be a power of 0. Negative 3 is going to have a power of 4. Now we have to go back and simplify all this. Okay, 1, well, forget about that. 2x to the fourth. Well, we have to do some spreading the love here. So we end up with 2 to the fourth power is 16. X to the fourth power. Anything with the 0 power is 1, so you don't have to write that. I mean, basically, you don't really need to write this in the first place. I just wanted to write that just to kind of show you how this works. But in the future, you probably don't even want to write the ones that have 0 powers. Okay, second term, 4 times, okay, we're spreading the love here. 2 cubed is 8, and then x cubed. And then we have negative 3 to the first power, which is just negative 3. Third term, 6, spread the love here, and I guess there, it's not really spreading the love there, but 2 squared is 4, and then an x squared. Negative 3 squared, the negative is being squared, so it's 9. Plus 4, 2x to the first power is still just 2x. Negative 3 cubed is negative 27. Plus 1, that's fine. 2x to the 0 is still 1, so we got 1 times 1 is 1. Negative 3 to the fourth power is positive 81. Okay, we go back and simplify, and we'll have our answer 16x to the fourth power. Okay, we got 4 times 8 times negative 3, which is negative 96 x cubed. 6 times 4 times 9 is 24 times 9 is 216 x squared. 4 times 2 times negative 27 is negative 216 x plus 81. We're finished. So this amount right here is what we would have gotten if we'd actually multiplied 2x minus 3 times 2x minus 3 times 2x minus 3 times 2x minus 3. I know that was a lot of work. I promise you it was way faster than doing it the other way. Okay, the other way you could do this is you could do this the binomial expansion method, which is pretty well exactly what we just did, but instead of looking it up in the Pascal's triangle method, you would just think to yourself, okay, since it has a exponent of 4 here, the coefficient of the first term will be 4 choose 0, and then you would have your 2x to the fourth power and negative 3 to the 0 power, which I won't even write. The second term would have a coefficient of 4 choose 1, and then we would have 2x cubed negative 3 to the first power, which I don't need to really write. The next term would have 4 choose 2, and then I would have 2x squared and negative 3 squared. The next one would be 4 choose 3, and then I would have 2x to the first power and negative 3 to the third power, and the final term would be 4 choose 4, and then 2x to the 0 power I don't need to write, and negative 3 to the fourth power. If you were to do all that, you get exactly the same answer. I'm not going to do that, but that's the binomial expansion method. I mean, in a sense, you could use the Pascal's triangle now to figure out what all these values are, so I don't know. I tend to focus on the Pascal triangle method. Okay, let's do this next one. We'll just do the Pascal triangle method. Alright, so you want to figure out what is your A, what's your B, and I guess what's your N, although it's not quite as important. I mean, it is important, but it's pretty obvious what it is. A is x squared, B is 2 divided by y, and N is 5. So how many terms are we going to end up with? 6 terms. Oh my gosh, it's going to be a lot of work. Let's look to see, let's use Pascal's triangle method. If we're interested in 5, raising some to the fifth power, then we need the fifth row of Pascal's triangle. So fifth row, 0, 1, 2, 3, 4, 5. I guess it makes sense, that's one below the fourth row. So 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. I'll write them down here. 1, 5, 10, 10, 5, 1. Okay, I'll try to go a little bit faster this time. First coefficient is 1, don't need to really write it. And then I have x, my a value is x squared, and that will be to the fifth power. Right? Because that's the power it's the whole thing's raised to. The second value, the b, will be raised to the 0 power, so you don't need to write it. Plus coefficient of 5, a value is x squared, it'll now be the fourth, and my y value, 2 over y, will now be to the first power. Don't need to really write the 1 there. Plus third term, third coefficient is 10, x squared is the a value, it's now at 3, and 2 over y is now at 2. Again, notice how they always add up to 5. 5, 4 plus 1 is 5, 3 plus 2 is 5. Next coefficient is another 10. X squared drops another power from 3 to 2. 2 over y gains another power from 2 to 3. Plus, next coefficient is 5. X squared drops down to 1, so I don't need to put the 1. And, 2 over y goes up to 4. And the last one has a coefficient of 1, you don't really need to write that. X squared's down to 0 power, you don't need to write that, so you only have 2 over y to the fifth power. Okay, spread the love here, or multiply, I suppose, power over power. Get x to the 10th, plus 5 x to the 8th, times 2 over y, plus 10 x6. Spread the love here, right? You can spread the love when you have multiplying or dividing, so you can spread love here. 2 squared is 4 over y squared, plus 10 x to the fourth power, over, spread the love, 2 cubed is 8, and y cubed, plus 5x squared, spread the love, 2 to the fourth is 16th, y to the fourth, plus, spread the love, 32 over y to the fifth. Final line of work here, x to the 10th, plus 5 times 2 is 10, x to the 8th, all over y in the denominator, plus 10 times 4 is 40x to the 6th, all over y squared, plus 10 times 8 is 80x to the 4th, all over y cubed, plus 5 times 16 is 80x squared, all over y to the 4th, plus 32 over y to the 5th. Done. A lot of work, but it is quite repetitive, so it's not too bad. Alright, what if you didn't want to know the whole thing? Like, what if it was something raised to the 12th power, like this question right here? I do not want to have to write out 13 terms. It's a lot of work. So what if I just want to know, like, the 10th term? Well, we've got a nice formula for that, and here's the formula. The formula to find a specific term is this. For a binomial expansion, a plus b to the nth power, the specific term is term k plus 1 equals n choose k, a to the n minus k, times b to the k. Determine the 10th term in the expansion of blah 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 blah. Okay, so the first thing you have to do is you have to figure out what k is. I know it's kind of weird. Where did this k come from? Well, we're talking about the 10th term, right? It says here, determine the 10th term. 10th term is the same as T10, right? Just like when we did arithmetic series and sequences last year, T10 means 10th term. And if you look at the formula, we're interested in tk plus 1. So if we're interested in the 10th term, the k value that would make 10 here is if k is 9. Basically, it's always going to be 1 less. The k value is always going to be 1 less than the term you're looking for. If I'm looking for the 10th term, the k value will be 9. The reason for that has to do with Pascal's triangle and the fact that we call things the 0 term. That's the reason we take 1 less. Okay, so we have our k. We need to know what n is. Well, that's no problem. N is just the exponent, 12. Guess we better figure out what our a is. Our a is 1. We better figure out what our b is. Our b is negative 2m. So all we do now is plug everything in. How we get the term is we do n choose k. Well, n is 12. Choose k is 9. Our a value is 1. raised to the n minus k, 12 minus 9, times, I suppose, or just in brackets, b, which is negative 2m, raised to the k power, which is 9. Okay, 12, choose 9. You could use Pascal's triangle, but you'd have to extend it a little bit because I didn't go down that far. Or you could pull out your calculator and do 12, choose 9. When you do that, you will find it is 220 times 1 to the third power times negative 2 to the ninth power. We've got to spread the love here, right? So we're going, if you want, you can even think of it as the negative, the 2, and the m. 9 negatives makes a negative, so it's definitely going to be negative. 2 to the ninth power, well, you can work that out if you want, or get a calculator. It's 512. And m to the ninth power. Okay, let's just look at that. 1 cubed is still just 1. So basically we have 220 times negative 512, m9. 220 times negative 512 is negative 112640, negative 112,640, m to the ninth power. That is what the 10th term is if we were to expand 1 minus 2m to the 12th power. And thank goodness we don't have to go 1 minus 2m times 1 minus 2m times 1 minus 2m 12 times. That would be horrendous. Last one, we do the same sort of thing. So remember, what we're looking for is the 4th term here. 4th term. So T4 is what we're looking for, and we equate it to TK plus 1, which means K is 3. As I said, it'll always be 1 less than the term you're looking for. Our N value is, what is that, 7 up there? Our A value is 3x. Our b value is 1/2, and again we just plug everything in. So let's make it so I can see the equation. N C K, N choose K, so 7 choose 3. A is 3x. Then N minus K, 7 minus 3. B is 1/2 to the K power, that's 3. 7 choose 3, you could use the Pascal's triangle if you want. 7 choose 3. Go to the 7th row. 0, 1, 2, 3, 4, 5, 6, 7. Choose 3, so go over to the third element or third term. 0, 1, 2, 3. There it is, 35. Already highlighted for us. Awesome. I think it's because we already did that exact one before. So we have 35. 3x to the 4th power. 1/2 cubed. We could do that right now. 1/2 times 1/2 times 1/2. Or if you want, spread the love. 1 cubed is 1. 2 cubed is 8. Then you need to spread the love here. So 3 to the 4th power and x to the 4th power. So you get 35 times 3 to the 4th power is 81. X to the 4th power times 1 over 8. You can't divide anything, but you won't be able to simplify. So you just go 35 times 81, which equals 2,835. X to the 4th. Keep the 8 on the bottom, and you have your answer. This is the 4th term in that expansion. Okay, be careful, go slowly if you need to, but it's very be methodical about it and follow the patterns, and you can do it. And I don't want this to disappear. There, it's back, right where it should be. And you're right where you should be, listening to math videos. Have a good day.